It all begins with something most people never think twice about: a roll of metal. Not just any metal, aluminum foil, but not the kind you'd use in your kitchen. This foil is destined to become part of the powerful little device that sits quietly in backpacks, pockets, or desk drawers, waiting for the moment a phone hits 1%. This is the positive electrode in a lithium battery, the very heart of a power bank. Before anything takes shape, the aluminum foil is carefully coated. It's not just dipped in any liquid. This mixture is engineered to the molecule. It includes active materials like ternary compounds and lithium manganese oxide. Conductive agents help electrons move freely, binders hold the structure together, and solvents keep everything just the right consistency. The mixture is spread evenly across the aluminum using a precision coating machine, forming a sticky black film. Once coated, the foil goes through a drying process where all that solvent evaporates, leaving behind a perfectly smooth layer of electrode material. It's during this drying phase that the real transformation begins. The same coating process happens for the negative electrode too, except copper foil is used instead of aluminum. And that slight change in material makes a massive difference when it comes to battery chemistry. After drying, there's no time to waste. The coated electrodes are passed through a roll press. The goal here is to squeeze the material thinner and denser. That not only saves space, but ensures a consistent structure, which is crucial for performance. A properly pressed surface reflects light, almost like a mirror. That shiny finish? It's a sign the electrode is ready for the next phase. Now the material is trimmed, or what they call slitting. Picture these wide-coated sheets being sliced into narrow, clean strips, each one ready to be turned into the inner workings of a battery. The edges are flawless, the waste is vacuumed up and recycled. It's clean, efficient, and surprisingly satisfying to watch. Once the slitting is done, the next step is tabbing. Here, small metal tabs are welded onto both the positive and negative electrodes. Aluminum tabs for the positive side, nickel tabs for the negative. These tabs will eventually be the connection points for the power bank's circuit board. But they're not just tacked on. Each weld has to meet specific tensile strength standards. If it's too weak, the battery won't survive assembly. If it's too strong, it risks damaging the thin electrode materials. It's all about balance. The machines performing these welds are tuned to microsecond precision, delivering just enough energy to create a bond without burning through the material. In a single shift, thousands of tab welds are performed, and each one must be flawless. Sensors monitor the current, pressure, and temperature in real time, flagging even the smallest anomaly. Sometimes a tab weld may appear perfect on the surface, but internal resistance tells another story. That's why additional electrical tests are often run after this step. Tabbing also sets the stage for how well the battery integrates into the larger power system. If the connection points are even slightly misaligned, it can cause serious issues during assembly. Operators often work under magnifiers, using cameras and screens to guide placement down to the millimeter. There's a visual rhythm to this stage. Clean, consistent welds lined up like stitches on fabric. Each spark from the welder is a tiny burst of precision engineering. Depending on the battery format, the tab length and position might change, but the core principle remains the same: strength without compromise. Sometimes the tabs are folded or bent to prepare for the next stage, and that bend needs to be perfect. Too sharp and it could crack under stress. Too loose and it might not fit properly into the final pack. In high-capacity designs, dual tab configurations are sometimes used to distribute current more evenly. That adds another layer of complexity, but also improves performance. Engineers often revisit the tabbing stage when optimizing for efficiency or improving battery longevity. Even the tab material itself is carefully selected for conductivity, durability, and cost. It's a small part of the battery, but a vital one. In many ways, the tabs are the silent heroes of energy transfer. And once this precise dance of welding and alignment is done, the battery is finally ready to be shaped into the energy core that powers a modern device. With tabbing completed, it's time to build the core of the battery. Using an automatic winding machine, the positive and negative electrodes are carefully wound together with a separator sheet sandwiched in between. The separator does exactly what it sounds like. It keeps the two electrodes from touching each other directly. If they ever did, it could lead to a short circuit, or worse, a fire. Winding this way ensures compact, high-capacity cells that are safe and reliable. But winding isn't where the checks stop. The wound battery cores go through X-ray inspection. And yes, that means the inside is scanned like luggage at an airport. This step ensures the layers are perfectly aligned and free of defects. Any core that doesn't meet the standard is removed before it causes problems later. Once the internal structure is cleared, the battery core gets its outer layer. It's inserted into an aluminum plastic film casing. A heated copper mold seals the edges to keep everything airtight. This film isn't just for looks. It's flexible, strong, and lightweight, perfect for the slim, modern design expected in portable tech. But the battery isn't alive yet, not until it's baked, literally. These cells are placed in a high-temperature vacuum environment. The goal here is to remove every last trace of moisture from inside the cell. Even microscopic droplets can mess with performance or create long-term safety risks. After baking, it's finally time for one of the most important steps: electrolyte injection. The electrolyte is a special liquid that allows lithium ions to move between the electrodes. Too much or too little, and the battery won't work as intended. So every battery is weighed before and after the injection. It's not a guess, it's science. Only the correct amount will ensure proper function. The electrolyte acts like the bloodstream of the battery, enabling the essential chemical reactions that store and release energy. But it's also highly sensitive. The environment has to be perfectly controlled. Humidity levels, temperature, even air quality, all of it matters. During injection, the battery cell is placed in a sealed chamber to minimize exposure to air because the electrolyte can react negatively with moisture. It's why even a tiny air leak can ruin a cell. The machinery used for injection has to be incredibly precise. We're talking about fractions of a gram here, micro adjustments to ensure just the right balance. After the injection, each cell is immediately reweighed to confirm the added volume. If the weight's off by even a fraction, the cell is flagged for review. The process isn't rushed. The goal is saturation, not speed. Some manufacturers even allow a short rest period after injection, letting the liquid naturally soak into the internal layers. This helps reduce trapped air and ensures better contact with the electrodes. The chemistry inside is delicate, and even distribution is key. Uneven electrolyte levels can cause performance inconsistencies or premature failure. The liquid itself varies depending on battery type, but it usually includes lithium salts and organic solvents, engineered for fast ion mobility and stability. There's a whole science around optimizing this formula for different battery uses. High-drain applications need faster ion transport, while long-life batteries need better stability. The containers used to hold the electrolyte are often nitrogen-sealed to avoid contamination, and operators wear gloves, goggles, and full suits to handle it safely. Even a small spill can be hazardous. Once inside the cell, the electrolyte doesn't just sit there. It becomes part of the chemical symphony. It must fill every crevice between the tightly wound electrodes, acting as a medium that makes the battery come alive. This one step, so quick in real time, can determine how well a battery performs for months or even years. That's why it's treated with the same seriousness as a launch countdown. When done right, the cell is fully charged, not just with liquid, but with potential. Once the electrolyte is in, the battery enters its aging phase. No, it doesn't mean sitting on a shelf and collecting dust. It's placed in a controlled high-temperature environment to allow the electrolyte to fully soak into the internal materials. This step helps improve the long-term performance and stability of the battery. Next up is formation. This is when the battery is charged for the very first time, and that first charge is crucial. During formation, a stable SEI layer forms on the electrodes. This layer acts like a shield, protecting the battery from degradation while allowing ions to pass through during charging and discharging. Without this step, a battery wouldn't last very long. Before final assembly, there's a final gas extraction step using a vacuum. Any residual gases are pulled out of the cell to ensure nothing contaminates the battery over time. After that, the battery is trimmed, removing excess material around the edges. This ensures the battery is exactly the right size to fit into a power bank. But performance matters most. So each cell goes through capacity testing. They're charged and discharged to measure how much power they actually hold. Cells are grouped by their capacity levels to ensure consistent performance in the final product. If one cell performs worse than the others, it's removed. Only the best make it through. Next comes the OCV, or Open Circuit Voltage Test. This checks the self-discharge rate. Batteries are left untouched for a set period, and the voltage drop is measured. A healthy cell will hold its charge. If it doesn't, it's flagged and pulled from production. At this point, you'd think the hard part is over, but the real show is just about to start. Now it's time to assemble the power bank itself. Inside the BlueTimes facility, these cells are lined up for a final round of checks. They go through visual inspections, voltage checks, and safety validations. Then 2 or more battery cells are paired together to form a single battery pack, increasing the overall capacity of the power bank. And this is where things really start to spark, literally. Spot welding connects the cells using nickel strips. These high-speed welds use intense heat and pressure to fuse the metal together. It's fast, loud, and dramatic, especially when sparks fly, but it's all controlled with incredible precision. These connections must handle both energy transfer and mechanical stress. Once the cells are connected, the brains are added. That means installing the protection circuit, also known as the BMS or Battery Management System. This tiny circuit ensures safety by monitoring temperature, voltage, and current flow. It's what keeps the power bank from overcharging, short-circuiting, or overheating. Without this, using a power bank would be a gamble. Now that the inside is complete, the casing comes next. This isn't just snapped together. An ultrasonic welding machine seals the plastic shell shut. Using high-frequency vibrations, it melts and fuses the case without using glue or screws. The result? A seamless finish that looks clean and feels durable. And once it's sealed, there's no going back. The case isn't meant to be opened. The power bank is almost ready, but it's not official until it's tested. The final device goes through more aging tests to simulate long-term use. It's charged, discharged, dropped, and shaken. And yes, there's even a drop test where the power bank is smashed against a hard surface to make sure it won't break or malfunction under real-world conditions. Only the strongest survive. For branding, there's a laser printing process that adds the final logo or product details. It's clean, fast, and permanent. And just like that, a brand new power bank rolls off the line. Sleek, compact, and ready to charge anything from phones to tablets and beyond. Behind every power bank is a journey of chemistry, engineering, precision, and innovation. And at the center of it all is BlueTimes, a company with over 18 years of experience in building smart, sustainable, and reliable energy solutions. As a leading OEM and ODM partner, BlueTimes doesn't just build power banks. They engineer trust, consistency, and performance. With patented designs, rapid development cycles, and factory-grade precision, their technology helps brands stand out while delivering the power users depend on every single day. From aluminum foil to circuit boards, from baking ovens to drop tests, this process is a reminder that portable energy isn't just about convenience. It's about innovation, it's about safety, and it's about turning science into something people carry in their pockets without ever thinking twice about it. And that's how power banks are made. Don't forget to like, comment, and subscribe for more behind-the-scenes looks into the world of tech, design, and innovation. It all begins with sand, not the golden beach kind, but a specific kind of silica sand, ultra-pure quartz, that gets refined into the glass that will eventually become the protective screen for the next-gen iPhone. Think about that for a second. The sleek slab in your hand once started life in a mine. That refinement process, those chemical reactions, those are the first steps in transforming raw earth into premium tech. From there, we move into the global supply chain, the nodes of sourcing, logistics, and manufacturing that underpin every model in the lineup. Next, the chip, the computer heart of the device, fabricated in advanced semiconductor clean rooms, often in Taiwan or Korea. The die is etched in nanometers, layered with transistors that number in the tens of billions. Once that wafer is sliced, packaged, tested, and shipped, it arrives at an assembly plant where thousands of precision machine tools and robotic arms await. It's here that the board is populated. RAM, flash storage, cameras, sensors, wireless modules, all placed with near-micron precision. The factory floor hums with conveyor belts, collaborative robots using vision systems, human workers performing joinery on flex cables and modules. It's a dance of man and machine, orchestrated to achieve both speed and zero defects. On the exterior, the chassis is made of aerospace-grade metal or ceramic glass composite, depending on the model. Milled, cleaned, anodized, coated, curved, each step adds to the premium feel. Meanwhile, the glass screen gets chemically strengthened through ion exchange processes. The surface atoms are swapped so that the glass becomes tougher, more scratch-resistant. Google this process and you'll find how even the early iPhones leverage this technology to stand apart. Night and day differences. Then there's the back glass, or finish, layers of paint, undercoating, laser etching logos, all handled in exquisitely clean, dust-controlled environments. A speck of dust can mean a reject. Waterproofing, dust-proofing, gaskets, seals, adhesives applied. Each port and each seam receives a pressure test. The device must survive spray, immersion, and still meet aesthetic standards. Internally, the battery is bonded and tested. The camera modules are aligned and calibrated. The lenses are inspected under multiple angles. The speakers tuned individually for frequency response. Wireless antennas positioned to minimize interference. This isn't mass production in the old sense. It's miniature precision manufacturing, optimized at scale. Then begin the lines of assembly. The main board is mated to the screen module. The chassis closes. Quality assurance stations check drop resistance, thermal performance, electromagnetic emissions. Software loads firmware. Sensors are calibrated. Cameras capture test images. A battery cycle runs. Each phone passes through dozens of gates before being boxed. You'll see workers affixing serial numbers, printing barcodes, and attaching packaging which itself has been designed to balance protection, sustainability, and branded experience. What's often overlooked is how much logistics matters in this system. Components must arrive just in time. Storage of parts is minimized to reduce obsolescence risk. The factory partners with air freight, shipping lines, customs brokers, and local governments. With recent shifts in global manufacturing, we're seeing factories not just in one country, but multiple assembly hubs moving from one region to another to avoid tariffs, supply bottlenecks, and geopolitical risk. Sustainability is also now part of the story. Recycling of rare earth magnets, cobalt from batteries, recovery of precious metals from failed units, all part of the life cycle. The factories include solvent-free paint booths, water recovery systems, solar arrays. When you hold a device, it's not just tech, it's the output of a global manufacturing ecosystem trying to balance innovation with responsibility. From the moment raw materials are mined to the moment the device is shipped out of the factory and lands in your hands, thousands of decisions have been made about design, materials, logistics, tooling, testing, assembly, packaging, shipping. Each one adds cost, risk, complexity. That's why the final product has its premium price, but also why so many users feel it's worth it. You're not just buying a phone, you're buying the culmination of global engineering, manufacturing, and supply chain mastery. Now think about you unboxing it. Every piece of packaging, the highlight color, the weight of the device, the subtle click when you insert a SIM, the first boot logo, those are user experience choices layered on top of technical choices. The factory delivered that experience, but the design studio envisioned it. From unseen tools inside the machine to the feel of that first swipe, the factory is the deliverer of promise. When you power it on, the operating system checks sensors, the chips coordinate camera functions, electrodes. The network module looks for signal, the display adapts to ambient light. It's seamless because the manufacturing process paved the way for seamless. Precision placement of antennas minimizes dead zones. High tolerance ensures alignment. Thermal management within the enclosure ensures performance under load without overheating. Without hundreds of microengineering decisions aligning, your experience would degrade. Beyond what you see, what you don't see is just as important. Beta testing in factories, screening out units that fail reliability tests, performing environmental stress screenings, heat, cold, humidity, drop impact. These steps ensure that when you buy it, it works in your environment, whether you're using it in a humid city, a desert, or a snow-covered town. The factory and QA answer to that real-world expectation. And let's talk about volume and risk. Producing tens of millions of units within weeks of launch requires factories to ramp rapidly, train staff, calibrate machines, source parts. If one supplier fails, alternate routing or backup production must exist. That's why manufacturing planning begins years before the final reveal. The assembly lines are laid out months ahead, robotic cells qualified, operators trained, parts warehoused. When the one more thing launches on stage, that phone arriving in stores is the visible end of a near-invisible global machine. Factor in costs, component shortages, currency swings, labor dynamics, transportation bottlenecks all pressurize margins. Factories can sneeze and the ripple reaches your wallet. That's why modern manufacturing strategies include inventory buffers, multi-sourcing, regional diversification. We're seeing that shift now with smartphone manufacturers who cannot rely on one country or one line to deliver the world's supply. Let's zoom back out and see how the factory concept itself has changed. It's no longer one giant factory in one place. It's a network. Some modules are made in Korea, shipped to India, others in China, shipped to Europe. Final assembly might happen in one country, refurbishment in another, packaging in a third, and logistic hubs connect them all. For this latest flagship, the network has grown even more geographically distributed, multi-sourced, automated, and responsive. That's the only way to meet global demand. Tight launch windows and premium margins. From the end user perspective, what does this mean? It means the device you hold has passed through more hands, machines, audits, and test cycles than most electronics in your home. It means that every aspect, from the feel of the side button to the warmth of the finish to how the camera captures color, was likely fine-tuned at a factory floor somewhere or in front of a CAD console months ago. It means that the final product is as much a testament to manufacturing discipline as it is to design genius. Before you send your new phone on its first charge, imagine the journey. The sand carved out of the earth, the quartz refined, the chip etched, the screens polished, the cameras aligned, the antennas tuned, the board assembled, the chassis pressed, the factory humming, the quality gates spanning continents, the packaging filled, the supply chain humming, and then a plane crosses the sky delivering it to you. That story gives new meaning to designed in and assembled in. It reminds you that in a world of global tech, your device is the endpoint of thousands of kilometers of parts, people, machines, and decisions. But the real marvel isn't just the machines or materials, it's the coordination. In Apple's factories, every movement is measured down to milliseconds. Cameras monitor workers' actions to ensure perfect synchronization with robotic systems. Algorithms optimize conveyor speeds and even control ambient temperature so adhesives cure at precise rates. Every screw, every connector, every cable follows an invisible script written by years of refinement. Engineers in Cupertino design, test, and simulate assembly virtually before a single prototype hits the production line. By the time the cables that charge phones, sync data, and keep devices running, they seem simple. But behind every strong, flexible USB cable is a fascinating process where ultra-fine copper, molten plastic, weaving machines, and precision tools come together in perfect sync. Right from the raw copper wires to the final bend test that breaks them, there's a whole world hiding inside every wire. It all begins with copper. Not just one strand, but 50 razor-thin copper threads that come together to form a single strong conductor. They're twisted or stranded into one bundle. It's not just about strength, though that matters. It's about flexibility. A single thick wire would snap with repeated bending. But twist 50 tiny threads, and you get the strength of a rope with the bendiness of a vine. This stranding process is a dance of precision, where every copper strand must flow in perfect alignment. And the machine that handles this, it doesn't pause, doesn't blink, just feeds the wires in, spins them with rhythmic consistency, and sends out perfectly stranded cores. Now, stranded wires alone aren't enough. These tiny conductors have to be shielded from the chaos of the world, electromagnetic interference, temperature shifts, friction. That's where shielding steps in. A wrap of aluminum foil comes around the stranded core, turning the cable into a mini fortress. This isn't ordinary foil either. It's ultra-thin, lightweight, but incredibly effective at bouncing off stray signals. Wi-Fi routers, Bluetooth devices, electrical noise, all of it blocked out. This shield ensures that when data flows, it flows clean and fast. Inside a typical USB cable, there are usually 4 internal wires, each one insulated, color-coded, and ready to transmit power and data. But before they can be bundled into the final cable, something clever happens. Talcum powder, yeah, baby powder, is dusted between these wires. Why? Because when the plastic sheath is extruded around them, they shouldn't stick together. Talcum keeps everything smooth, letting the wires move slightly within the sheath without damaging each other over time. This tiny step makes a massive difference. Without talcum, the plastic sheath could cling to the wires too tightly, causing stress points that wear down over time. Even a millimeter of movement can protect a cable from breaking internally. And it's not just sprinkled on randomly, it's applied with specialized dispensers that coat each wire evenly, ensuring no clumps or bare spots. It's almost invisible when applied, but its presence is crucial. This powder layer acts like a silent guardian, reducing friction, absorbing micro vibrations, and even helping during the cooling phase after extrusion. It also plays a role in how the cable handles long-term use. When the cable bends, twists, or stretches, the internal wires can glide subtly inside the sheath instead of locking up. This gliding motion is what extends the life of the cable, especially under daily stress like being coiled, pulled from pockets, or jammed behind desks. The cable remains flexible, not because the outer sheath is soft, but because the inside isn't fighting against itself. Even during testing, cables with properly applied talcum show fewer failures in the flexibility and stress tests. It's such a small addition, but it's like adding lube to an engine. The system just works better. It's another example of how the tiniest details in manufacturing are often the most important. Most users will never know it's there, but every time a cable survives another bend, another twist, another accidental yank, talcum deserves some of the credit. And then comes the extrusion. Picture a hot pressurized machine forcing molten plastic over the wire core, like squeezing toothpaste onto a brush. The sheath forms instantly, but it's soft at first, so it hits a cooling tank right after, where cold water helps it solidify into that familiar flexible outer layer. Once it's cooled, a quick check ensures the diameter is just right. Too thick, and it becomes clunky. Too thin, and it risks breaking. Consistency here means quality later. At this point, the cable's starting to look familiar, but it's still missing one of the most critical layers, the braid. Now this is the part that's honestly mesmerizing to watch. A USB data cable braiding machine comes to life like a maypole dance, spindles spinning, threads flying as nylon or polyester fibers wrap around the cable with hypnotic speed and precision. It's not just for looks, though yes, the nylon does come in a rainbow of colors and gives cables that textured premium feel. But it's also about strength. This braided layer massively improves wear resistance. Drag it across a desk 1,000 times, stuff it into backpacks, twist it in weird angles. That nylon shell can take it. On some machines, up to 48 carriers spin at once, moving at speeds as high as 360 RPM. Creating an intricate woven layer in seconds. And the best part? It's all automated. Just feed in the cable, set the bobbins, and watch the machine perform its dance. What's even cooler is that this braided shell isn't just about toughness. It adds electromagnetic shielding too. especially when woven with tin-plated copper or aluminum magnesium wire. In some cases, the shielding efficiency reaches 60 decibels at 1 gigahertz, which means it's blocking out a ton of interference. That's not something you see, but it's the reason why your cable works reliably in noisy environments. Of course, machines do a lot, but not everything. Human hands still play a role, and a crucial one. There's finesse needed in certain stages that even the most advanced robot arm can't replicate. Not yet, anyway. For example, when it's time to attach the USB connectors, people often prep the cable ends manually. The outer sheath is stripped, the wires exposed and trimmed with precision, then comes the soldering. USB Type-A, the classic rectangular connector, and USB Type-C. Flux is applied to ensure strong oxidation-free joints, and the heat must be just right. Too hot, and you'll scorch the wire. Too cool, and the solder won't bond correctly. That delicate balance is something no machine can fully feel. It takes human intuition. Some factories have semi-automated soldering stations where machines assist with the repetitive motions, but the prep work and final inspections are still handled by technicians. Technicians often check each unit by giving a firm tug after assembly, verifying the joint's integrity without needing software or sensors. So while machines speed things up and keep the process efficient, the hands-on work adds the reliability. Every cable is checked for visual flaws, uneven sheaths, misaligned connectors, discoloration, or anything that might hint at deeper issues. These aren't just cosmetic checks. A small flaw on the outside can mean a big problem inside, so this final pass ensures that every cable not only works, it looks like it should. Now, here's where things get really serious. Ever wonder how cables claim to survive thousands of bends? There's an actual robot that tests that. It bends the cable again and again in tight angles, simulating the way users twist and turn them in real life. This machine does the same movement over 10,000 times. Eventually, even the strongest cable will snap, but the goal is to find out when. That breaking point tells manufacturers whether their materials and designs are truly holding up to real-world use. The test rig looks simple at first, just a robotic arm moving rhythmically, but it's doing something vital. Each bend happens at a precise angle with measured force, replicating the common abuse a cable takes, being yanked off desks, coiled and uncoiled, twisted while charging in bed, or bent at weird angles inside backpacks. Over time, these small motions can cause internal fractures, even when the outer sheath looks perfectly fine. During this endurance test, high-speed sensors track the resistance and continuity of the cable in real time. The moment even one internal wire breaks or loses connection, the test stops. The engineers then pull that cable apart and inspect where and how it failed. Did the copper strand snap? Did the solder give out? Or did the plastic stretch and shift too much? These failures become lessons, directly influencing future designs. Some cables are tested in batches of hundreds. Results are logged, charted, and compared across materials, manufacturing variations, and even different braiding techniques. It's not just about pass or fail, it's about understanding durability in the harshest conditions. Brands that advertise higher bend counts are often those that invest heavily in this type of stress testing. What's even more interesting is how certain reinforcements, like braided nylon and flexible strain relief designs, consistently extend cable lifespan. In some premium cables, the breaking point doesn't come until after 20,000 or even 30,000 bends, nearly triple the average. Those stats aren't just marketing fluff, they're born from months of physical punishment in testing labs. And it's not just one bend axis being tested. Some setups test side-to-side motion, some test vertical strain, and others rotate the connector while bending the cable, which is a common movement when devices shift during charging. All of this helps build a realistic picture of how a cable survives in hands, pockets, and under desks. At the end of the day, these repetitive motions separate cables that just look good from those that actually perform. That little sticker saying 10,000 bend lifespan? It's backed by relentless testing, mechanical arms, and teams of engineers watching every snap and shift. It's the kind of behind-the-scenes torture that makes sure the cable you grab in a rush doesn't fail when it matters most. Cables that survive longer get rated higher. Some of the best can handle over 30,000 bends. Others start failing around 10,000. Either way, this test separates the strong from the weak and shows whether the braided nylon, the stranded copper, the soldered joints, and the injected casing all do their job as one solid unit. And in the end, it's not just about surviving, it's about delivering. Some cables, like high-performance USB-C models, offer fast-charging capabilities up to 66 watts. That's enough to power tablets, laptops, even some small appliances. And to hit that kind of power, everything has to be built to spec. From the wire gauge to the shielding to the soldering and connector type, every part matters. That's the full journey. From the raw copper strands all the way to the final bend test and performance rating, it's a mix of science, engineering, craftsmanship, and high-speed machines working in harmony. And even though a USB cable might seem small, the technology inside is anything but. So the next time one of those cables powers up a phone, syncs your files, or charges a smartwatch, that's not just a wire. It's a result of meticulous design, careful testing, and some truly mesmerizing machines spinning, soldering, and shaping the strongest wire that lives in your pocket. Like this deep dive? Go ahead, hit that subscribe button, and join the channel for more behind-the-scenes breakdowns of how the tech you use every day is built. There's always more to uncover, and you're going to want to see it. Imagine lining up every Duracell battery made in a single year. You'd wrap around the Earth more than twice. That's a mind-bending number of copper tops powering everything from remotes to smoke detectors. But how does Duracell actually pull off this insane pace of 10 billion batteries a year? Think about how invisible batteries are to us. They're everywhere. The remote you throw at the couch cushions, the flashlight you only remember when the power goes out, the smoke detector that suddenly starts chirping at 2 a.m. and makes you question every decision in life. We take them for granted until the moment they die, and then, suddenly, it's a crisis. Duracell has become the name people trust in those exact moments, partly because of that iconic copper top design, but mostly because for decades they've built a reputation for reliability. And yet, their story doesn't start with your TV remote or your kid's toy. It begins nearly a century ago and in a completely different world. Back in the 1920s, Samuel Rubin wasn't dreaming about AAs and AOAs sitting in blister packs. He was a scientist focused on developing better battery cells for specialized equipment. Alongside businessman Philip Rogers Mallory, they formed a company that at first made mercury batteries. And while mercury doesn't sound like the most user-friendly ingredient today, back then it was a breakthrough. These batteries became especially valuable during World War II, when the military needed cells that wouldn't give up in tropical humidity. The devices they powered had to keep running, no matter the climate, no matter the conditions. That reliability in the middle of war zones built the foundation for what would later become Duracell. The real shift happened in the 1960s. The company pivoted toward alkaline batteries, the kind you and I use every single day, and they needed a name that captured the promise: durable plus cell, Duracell. It was simple, but it was a promise. These little powerhouses would last longer than the competition. That brand identity solidified even further in 1973 when they rolled out the copper top design. Suddenly, you didn't even need to read the label to know it was a Duracell. It was sitting there in every grocery aisle, shiny and confident. That little bit of metal wasn't just branding, it was genius marketing that burned the image into consumers' heads. Ownership of the company bounced around over the years. First Kraft, then Gillette, then Procter & Gamble. Today, it's owned by Berkshire Hathaway. Yes, that means Warren Buffett, arguably the most famous investor alive, controls the batteries in your remote. You can almost picture him smiling every time you buy a 4-pack, knowing that even in the age of smartphones and high-tech gadgets, the humble AA battery still makes the world go round. So what actually makes up a Duracell battery? On paper, the recipe sounds like a science experiment that you'd probably fail in high school chemistry. Zinc, manganese dioxide, potassium hydroxide, graphite. Wrap that in steel, cap it with brass. Done. Except, of course, it's not nearly that simple. Zinc acts as the anode or negative terminal. Manganese dioxide is the cathode, the positive terminal. Potassium hydroxide is the electrolyte, the part that lets ions move back and forth. The outer casing is nickel-plated steel, tough enough to handle the chemical reactions inside while keeping everything sealed away. And that copper top? It's not just decoration, it's a nickel-plated brass cap designed to help conduct electricity cleanly into your device. Now, lots of companies could throw these materials together and call it a battery. But Duracell's entire reputation rests on the fact that they don't just toss stuff in a mixer and hope for the best. They use proprietary additives, precise formulas, and rigorous quality control that ensures consistency across billions of units. Every batch of raw materials gets tested before it even enters the production line. If the zinc isn't pure enough, if the manganese dioxide isn't up to spec, it doesn't make the cut. That's how they guarantee that whether you're buying a Duracell in Georgia or in Belgium or in China, it'll perform exactly as expected. And speaking of Georgia, Duracell's flagship factory in LaGrange is basically a cathedral of battery making. Imagine a production line moving so fast it pumps out 300 batteries every minute at each assembly station. Multiply that by multiple lines and you're looking at over 3,500 finished units per minute. It's like popcorn in the microwave, except instead of a snack, you get enough power to keep half the gadgets in your house alive. The process starts with preparing the cathode mix, which is basically a carefully engineered cocktail of manganese dioxide, carbon, and secret ingredients Duracell doesn't talk about. This mix is pressed into little rings or sleeves that form the outer portion of the battery's core. Meanwhile, zinc powder is prepared with its own additives to make it more conductive and less prone to corrosion. These two powerhouses, the anode and cathode, are kept apart by a separator, a thin paper-like material that lets ions pass but stops the two from directly touching. Think of it like putting up walls between roommates who really shouldn't be living together but still need to share the Wi-Fi. The steel casing, which will become the body of the battery, is formed and nickel-plated to fight corrosion. The copper tops are stamped out of brass sheets, polished, and set aside for later assembly. Then comes the moment when everything comes together. The cathode rings slide into the casing. The separator goes in next. The zinc mixture fills the center. A carefully measured amount of potassium hydroxide electrolyte is added. And finally, the copper top is attached, along with a plastic insulating washer to make sure the positive and negative sides don't accidentally connect. Sealing the unit is a critical step. Too loose, and the battery could leak. Too tight, and internal pressure could cause problems. Duracell has spent decades perfecting this process. Once sealed, the battery moves straight into testing. Unlike some rechargeable batteries that need forming, alkaline cells like Duracell's are ready to go as soon as they're built. But that doesn't mean they skip testing. Oh no. Every single one faces a gauntlet of checks that would make a Navy SEAL sweat. High-speed cameras look for visual defects. Automated systems measure voltage, resistance, and capacity. Samples from every batch are tortured with stress tests, extreme temperatures, accelerated aging, and leakage tests that simulate the worst conditions you could throw at them. One of Duracell's most important promises is that their batteries won't leak and destroy your expensive gadgets. That's why they put every unit through conditions harsher than anything you'd see in normal use. It's like training for the Olympics just so the battery can live a quiet life inside your garage door opener. Packaging is another area where Duracell has flexed its muscles over the years. When they rolled out Duralock technology, promising a 10-year shelf life, it wasn't just a marketing slogan, it was a legit shift in how batteries were preserved. By sealing them more effectively, Duracell made it possible for people to toss a pack in a drawer and still expect it to work a decade later. That's not just chemistry doing the heavy lifting, it's smart packaging design working hand in hand with the product itself. And they didn't stop there. They added little power check features so you can actually test a battery before you put it in your device. It's like a sneak preview that saves you from the classic, "Is it the remote or the battery that's dead?" guessing game. For smaller coin-style batteries, Duracell went one step further and created child-resistant packaging. Anyone who's ever dealt with toddlers knows they'll try to put just about anything in their mouth, so making sure those shiny little discs are locked behind tough blister packs is a lifesaver. Literally. Sustainability plays a growing role too, and Duracell has been quietly reshaping how its products reach us. Over the years, they've cut down on excess packaging, ditched unnecessary plastic windows, shrunk the overall pack sizes, and boosted the amount of recycled material they use. Their philosophy is straightforward. When you're selling billions of packs every single year, even small changes add up to massive differences. Less plastic, less cardboard, less waste. It's a ripple effect that becomes a wave when you're operating at Duracell's scale. And it's not just what you see on the store shelf. Inside their factories, like the flagship plant in Georgia, they've taken sustainability just as seriously. That facility has committed to sending zero waste to landfills, which means everything is either reused, recycled, or repurposed. They've also slashed water usage by millions of gallons annually through efficiency upgrades. For a company that runs production lines day and night, cutting that much resource use is no small feat. These shifts might not be as flashy as the copper-top design, but they matter, and they show that even in the world of disposable batteries, there's room for responsibility. Duracell isn't stopping at alkaline either. The copper top may be their superstar, but behind the scenes, they've been steadily building a lineup that covers just about every corner of modern life. They've got rechargeable batteries for people who hate running to the store every other week, ultra-tiny hearing aid batteries that pack a surprising punch, sleek power banks that keep your phone alive when you're traveling, and of course, the Optimum line. That one's built for the gadgets that seem to inhale energy, high-drain devices like game controllers, motorized toys, and fancy flashlights, or for anyone who just wants their batteries to hang in there a little longer before giving up. What makes it impressive is how far the chemistry itself has come. The stuff inside today's Duracell cells is light years ahead of what you would have bought off the shelf even 10 years ago. They've squeezed out more power, stretched the shelf life, and made the whole package more reliable, all without changing the size. So your AA battery still looks like the same old AA battery, but it's been hitting the scientific gym behind the scenes. It's a little like upgrading your phone every few years, except your batteries keep evolving without forcing you to learn a new charging cable. They just keep slipping into the same remote slot, the same flashlight, the same controller, only now with extra endurance tucked inside. Now you might be thinking, this is all great, but it's still just a battery. Does it really matter? The answer is yes. In disaster zones, when the grid goes down, batteries keep radios alive, flashlights shining, and medical devices working. Duracell even has a rapid response program that delivers free batteries to areas hit by natural disasters. In developing regions where power grids are unreliable or non-existent, a simple battery might mean a child can study after dark, or a family can run a radio. That long shelf life suddenly isn't just a marketing feature, it's a lifeline. Economically, Duracell's global empire supports thousands of jobs directly and many more through supply chains. The factories not only power your gadgets, they power local communities. And that's part of why Duracell has managed to stay not just relevant, but dominant in an age when technology is constantly shifting. From its unlikely beginnings in the 1920s through military breakthroughs in the 40s to consumer dominance in the 70s, and now as a global powerhouse under Berkshire Hathaway, Duracell has built its name on one simple promise: reliable power. Billions of times a year, that promise gets fulfilled in devices all over the world. So the next time you pop a copper top into a smoke detector or shove a couple into a game controller, remember the journey it's been on. From carefully tested raw materials through high-speed assembly lines, brutal quality control, and into packaging designed to keep it fresh for years. It's more than just a little cylinder of chemicals. It's 100 years of innovation squeezed into the palm of your hand. And if you enjoyed getting an inside look at how something so small makes such a big impact, don't forget to hit like, drop your thoughts in the comments, and subscribe for more stories like this.